Welcome to How to Prepare Your Models for Simulation, making the most of your FEA and CFD. Before we get started, we're going to go over a little bit about M2 Technologies. M2 Technologies is a consulting firm focused on productivity, improving manufacturing process efficiency, and reducing manufacturing costs. Using generative design and best-in-class manufacturing and asset management processes, our team of industry experts can help you become more sustainable, more profitable, and more prepared to meet the demands of urbanization in a rapidly changing world. We work in the fields of BIM for manufacturing, asset management, process optimization, and data management to bring the best technology and workflows to our customers. We partner with industry leaders such as Autodesk, Panzura, Eagle Point, and Bluebeam. Our services include CAD management, simulation, generative design, CIO advisories, and training. My name is Tristan Gunderson. I will be presenting today. I work with clients to bring the latest of technology and workflows to their business. Today we'll be covering techniques for preparing models for simulation, setting up studies, refining mesh, assessing results of studies, and lastly, how to refine those studies. In this, we'll be looking primarily at FEA and CFD. Both of these are computer-based simulations that allow us to rapid prototype our designs. Finite element analysis works by taking structural components and breaking them into elements and nodes so that we can calculate the stresses and change across the component. It's used for solid components and has studies for linear and nonlinear stress, modal and frequency response, impact analysis, heat transfer, and much more. And then computational fluid dynamics works similarly to FEA, but is designed to look at how fluids react and interact with solids. Within CFD, you can use solid components, fluid volumes, and even simplifications to model pumps and fans. We can use this to look at fluid flows, reactant forces, and again, heat transfer. To do so, we will be looking at how to use these within Autodesk Inventor Nastran and Autodesk CFD. Start by preparing the model. One of the largest drawbacks with simulation is the time it can take to run a complex study. What we're going to be doing is looking at some techniques to reduce the mesh count and lower that runtime. We can start by isolating the area of interest. If you have a large model, it is going to be running calculations across the entire assembly or component, regardless of where the area of interest or max and min forces are. So we can start by reducing to a single instance of a component or a subassembly if that's the area where the forces are being applied. From there, we can suppress additional components in order to isolate the area where we need to be focusing. This works largely the same within a part, where we can trim off large sections of geometry from our model. We usually do this by creating a new copy of the model before we bring it into the FEA, so any changes we make aren't carried into the part itself. We can trim large sections of the geometry either outside the area of interest if we are looking at, for instance, a flange on a larger part, we can remove the majority of that geometry and just leave the flange where the forces will be present. And then we also can remove geometry if there's planes of symmetry. If that's the case, we can slice the component in half and use constraints to represent the other half of the model. This will allow us to have half the mesh count we would with the full model. Our next step is to simplify the model. For assemblies, we can do this with a shrink wrap or simplify. These tools will help us to suppress any small components, as well as remove any small features that aren't needed, such as holes that are away from the area of interest. We can do the same thing with a part model by suppressing different part features. Lastly, once we've removed everything that we don't need, we can add in additional features or parts to help better represent the case we're studying. If we are looking at the forces within a connector, such as a bolt, we can place that into the model in order to study it. We also can add fillets to any sharp edges that are causing issues, and split faces to create a smaller section in which to apply constraints or loads. And lastly, if we're working with CFD, we can either create an internal volume for the fill, or we can create lead-ins and lead-outs to help us to represent a laminar flow going in and out of our part once we're done. Here we have a few examples of how to prepare our models. We have our original assembly of a pipe configuration bolted together. If we're looking at the forces in the bolts when they're in tension or even shear, we actually can pull a single subassembly to represent these forces along all of them. Or if we're looking at compression forces, we can use the shrink wrap or simplify to remove the bolts and bolt holes entirely and just focus on the structural components. Nextly, if we isolate a single part, we can again simplify by removing the bolt holes. And if we're putting it in CFD, we can model the leads in and out of this pipe to achieve that laminar flow. Once we have finished our models, we can set up the simulation. We start by creating idealizations. In Nastran, the default idealization is a solid 3D solid idealization. We have two other options we can use for these idealizations. We can create a line element for components that have a constant cross-section by defining the cross-section in the table seen. Or we can create a planar surface to represent any kind of sheet metal or surface with a consistent thickness. Both of these idealizations allow for a much smaller node count with similar results. Next, when working in CFD, we can define internal or external volumes using the void fill or by creating an external volume. This is usually used to represent our fluid, either the air or water surrounding or flowing through a component. This can also be used with the lead-ins and lead-outs if they create a cavity inside the component. By setting them to the same material later on, it'll act as a single fluid. Next, we can look at where we're placing our loads and constraints. It's important to remember that loads and constraints are going to hold steady a certain part of the model. If we're placing a stiff constraint on a bolt hole, that hole is not going to be able to move and can cause stresses that wouldn't be present in a real model, which would be able to deflect. So it's important to look at where we're placing these constraints so that they don't create an unreal stress. Ideally, we will place our constraints and loads away from the area of interest, but in a way that still represents the actual fixture. If you aren't able to avoid placing them away from areas of interest, try running two different studies with the loads and constraints flipped in order to get a better idea of the actual results. Lastly, we can set up initial conditions. Initial conditions are especially helpful in a heat transfer study, as we need to set an initial temperature in order to study how the temperature changes from there. Initial conditions are very important in setting these initial states of models that are either under pressure to begin with or with a temperature. Lastly, before we run, we need to define the mesh. This is where the refinement for how long a study is going to take really comes into play. The mesh is going to define where the calculations and the interactions between mesh points is taking place. You can see in this picture we already have 3 rings split around our bolt holes. This is to model where the washer will be interacting with the flange. We start by setting our default mesh settings. We can set it to coarser or finer depending on our needs. A finer course will result in a higher mesh count, which will take longer to run, whereas a coarse mesh has a tendency to have less accurate results. Now, this isn't to say that a fine mesh will always be more accurate, as different mesh counts can result in unreal results regardless of how fine or coarse it is. The key is to play around with this mesh count in order to find the ideal settings to get results. Once you apply it, you'll get a general mesh. You can see in the bolt holes and along some of the surfaces where the mesh is creating linearizations across rounded surfaces. In the large radii, this shouldn't be a problem, but can cause more of an issue where we have the smaller radii. What we can do to fix this is we can come in and add mesh controls to define a finer mesh around those areas. We can select vertexes, faces, or edges to define this finer mesh. If we try and set this to a coarser, it'll default to the standard mesh settings. We are only able to use these mesh controls to set areas to be finer than the general mesh. Once we do so, we can see we've created a finer mesh along the fillets and where our washers will interact with the part to get better results at those locations. And lastly, once we've run our study, we can analyze our results. Here we can see 2 results on the side. We'll notice in the top one that we're getting a large gradient across our mesh as it goes around the bend. This is because we have a very large mesh size for a small radii. We can then go back in and use mesh controls to get a smoother gradient going around the bend where we're getting our forces. We can also go back and add fillets to any locations with sharp edges that are causing errors. or we can edit our constraints and loads to different placements if they are causing issues, or change the values if needed if we are well beyond the area of our limitations. Lastly, when working with any kind of transient problem, we can edit the time steps and the iterations to run internally. Running large time steps and few iterations can cause the model not to properly update before the next time step and get inaccurate results. However, it's important to know the more iterations you run within time steps, the longer it's going to take. So it's often recommended to run a quick study to begin with to make sure that all of your settings are acting the way you would expect before running a long study, possibly overnight. Thank you for joining us for this webinar. If you have any questions or would like to talk to a representative, you can contact us at our website or by email or phone. Thank you.